Hello everyone. I am Debanjali Chatterjee, a PhD student at the Energy and Transport Sciences Lab at Purdue University and the president of the ECS Purdue Student Chapter. Welcome back to our fall webinar series on solid-state batteries and electrochemistry. The ECS Purdue Student Chapter comprises of over 20 student members led by the chapter officers under the guidance of the Chapter Advisory Board. Professor Partha Mukherjee from the School of Mechanical Engineering at Purdue is our lead faculty advisor. We have Dr. Judy Jeevarajan, Vice President of Research at Underwriters Labs as our distinguished industry advisor. Professor Rebecca Chase from the School of Mechanical Engineering and Professor Julia Laskin from the Department of Chemistry at Purdue are our co-faculty advisors. In spring 2021, we conducted our signature webinar series on women in electrochemical sciences and engineering, which was exceptionally well received and appreciated in the scientific community. Inspired by its success, this semester, we have launched a webinar series on one of the hot topics in energy storage research, which is solid-state batteries and electrochemistry. Today, the speaker for our concluding webinar for this semester is Dr. Jagjit Nanda. Dr. Nanda is a distinguished staff scientist and group leader of the Energy Storage and Conversion Group at Oak Ridge National Labs Chemical Sciences Division, with 20 years of experience in energy storage and battery materials. He holds a joint faculty appointment in the Chemical and Biomolecular Engineering Department at the University of Tennessee, Knoxville. He is the co-editor of the Handbook of Solid-State Batteries along with Nancy Dudney and William West, and has co-authored more than 200 journal and technical publications in the topic of batteries, solid-state electrolytes, and electrochemical interfaces. Dr. Nanda is a fellow of the Electrochemical Society and winner of 2 R&D 100 awards in the area of batteries and supercapacitors. Today, he will be speaking on evolution of electrode-electrolyte interfaces in all solid-state batteries. Dr. Nanda, we look forward to your talk.
Thank you, Devanjali, for nice introduction, and also thank you, Partha, my good friend, colleague, and collaborator, for a good introduction. And I thank the ECS Purdue chapter members for giving me an opportunity to speak to this afternoon. And you know, the way I want to make very sure that I want to this seminar to be very informal, and you can, you know, sometimes if you feel something not clear, you can even, you know, raise your hand or, you know, ask a lot. So I'll make sure that I'll have enough Q&A. So I plan to give a 40-45 minutes so that we have enough time for a more like a discussion, because more questions I hear or things, it will be much better than just me talking over PowerPoint. That's something which I think you are all used to, and maybe a little getting bored today nowadays because of extended non-travel and hybrid conferences, so on and so forth. Anyway, so it's my pleasure again to talk about things. It's always the team first. You know, we have National Lab. We have several staff members, very senior and at different level, and students contributing to what I'm presenting today. And so this is the team. I'll move on. So a couple of slides for the sake of students, who we are and what we do at Oak Ridge, just a few minutes. So we are a big energy science lab for the Department of Energy. We are constantly growing. We have some unique signature, which Partha knows very well, and few others, that we were good in a couple of things among the DOE National Lab and the international level in terms of our computing capacity, material research, and, you know, neutrons. These are really the best things that we do. What attracts me here is a big materials program and energy, and the solid history of solid electrolytes and thin films at Oak Ridge. That brought me here about 13 years back from Ford Motor Company. Again, we work on all the important topic, which are the national priorities. and basically you can see the transportation and the grid are the major area where energy storage is definitely a important aspect. But with decarbonization, we have thinking about other areas where energy storage can also lead to decarbonizing to meet our 2035 goals of reducing greenhouse gas emission by 50%. And at 2050, we want to be a net zero carbon economy. These are very tall orders, but as a role of a national lab, they eventually was asking that why we work on a national lab, not in a university. I said, here we are mission driven and we need to work as a bigger team to address bigger challenges. We do work with university and industry successfully, but we have taxpayer dollar at work here. All right, we have something to show that we have huge facilities like any national lab. We have high flux neutron reactor. This is the continuous neutron reactor. We have again I think okay, and this is the spallation neutron center, pulse neutron center for doing material research, biological research, and host other research. And we are this area is the second neutron target station being added, so it's going to be globally the biggest neutron research anywhere done in the world. So enough of the advertisement now. So now I'm going to sort of ask whether anything fundamentally has changed in battery fabrication and techniques, the way we think about batteries over 200 years. Now, this is my favorite slide. I like to challenge and think about. Now, if you think you may have seen this slide this picture long time when Volta had, where what you have always is a sandwich structure. You have two different electrodes and a soaking electrolyte separator to electrical isolation, and then you can run it in a series and you get a cell voltage. But if you see the modern days batteries, I don't think, except new materials and few things, the geometry and architecture has not changed much. You can see that you have still a bigger size layered planar electrode of some thickness, and you have still the soak separator, and you have some pouch cell on the format, and you stack it up. So yes, there is a lot of improvement, but there is also open for much more innovation in the form factor, in terms of designing and the electrode layers, in terms of how you can go to 3D structures. So there is much more innovation in my things to be made. And so the topic is lithium metal or solid state batteries. The question is, where does we want to go and why? So there is a big reason here why we need to go to lithium metal or maybe lithium sulfur type solid state cells. This is where we are going there right now. Silicon voltage, high voltage silicon is sort of getting ready. I think still we have calendar life issues there in silicon to be solved. Cycle life looks okay, but we have still challenges of calendar life. But anyway, if you see today, we are just at a stage of the energy density in terms of 275 to maximum 280 kilowatt per hour, and if you look at the progression of this slope here, you can, with the 30%, again, this is backpack model from Argonne. I'm not saying this is a perfect model, but this gives us a really good estimate of where with silicon, where you want to go. But if you want to leapfrog, you can see that with much lesser cost per kilowatt hour, then we need to go to lithium metal and solid state cells. So that's the reason and motivation why we want to really go there in terms of safety, obviously, in terms of energy density, and also potentially the cost. But again, it's potential. Uh, Again, so let's go back to the meat of this talk today. So today I want you to give you a flavor about what are the challenging issue of the electrolytes, the interfaces, and also I'll give you a tutorial of how to synthesize something in the lab, electrochemically make it, synthesize it, fabricate it, design it, test it, and all that is you do, and you explain at each step the challenges and the science directions and the optimization at each step. So it will be more like an online tutorial of synthesis, how to make it, how to fabricate it, that we do routinely in the labs here, small form factor, even slightly larger form factor as well. Anyway, this slide tells you what are the challenges of the solid electrolytes that some of you may already know, and what are the material solution. And it's a little dated, but it's still, very, very relevant. And this spider chart tells you that there is no electrolyte that you think can meet all the attributes here. What are the key attributes here? You can see as the coordinate of the spider plot is that a lot of materials, for example, have good thermal properties, but some have poor thermal properties. Some have less processing ability, brittle, and fail in mechanics. So I'll come to all these attributes today as we go along those different things. And but the way the failure mode of a solid electrolyte at the interface between lithium anode and a cathode is basically these attributes. So I'm expanding the material base here to give you a broader spectrum of what kind of solid electrolytes that's present. And the motivation for giving this slide is that you can see that the maximum area, obviously one idea is the maximum, the way this touches this contour plot is preferable, but you can see there is still gaps. There is no unique electrolytes that can solve your issues. That essentially means we may have to go for a hybrid type of material that good from terms of processability, in terms of large electrochemical window, oxidation stability versus reduction stability, chemical stability. So basically there is a lot of choices here. The question is whether each electrolyte system like the other electrolyte system. That's the key here, without having so much resistance or incompatibility. But there is a whole class of material, from oxides to sulfides to hydrides to halides, thin film, and polymer, composite and polymers. So, but again, this is the whole spectrum of solid electrolytes that's available at present to the community to build from here with solid state batteries. So basically the requirements are, is pretty complex and pretty demanding. So we need to find a solid electrolyte that needs to have a sort of superionic conductor, -3, -4 Siemens per centimeter, greater than -4 at least. And you may need to make sure that you can make it a battery, so it would have robust mechanical properties and processing ability to do ability to make it thin sheet. And then you have to make it tough and compatible and wettability and other things, so that it has the can sustain a critical current density or critical current without forming shorting or dendrites. Plus it should have chemical stability with the lithium metal as well as cathodes. So the demand of what I was saying is to need to for a composite solid electrolyte. So that's something we need to keep in mind. So it's all about solid state batteries, all about interfaces and interfaces. the point I'm making here to all the students is that, whether you think of an all solid state battery or even a thin film battery for consumer electronics, or even people who are doing 3D batteries, we need to carefully engineer the electrolyte electrode interfaces, because this is basically solid interfaces. That essentially means we need to have the optimal ionic conductivity and make sure that ions can conduct at the interfaces without much scattering in terms of proximity and the finite diffusion distance that the ion need to reach. At the same time, the electrons has to get transported back to the current collectors, going back without causing significant polarization. So this is irrespective of the type of geometry you think, interfaces are the key. Now the interfaces can be defined into two. One is anode solid electrolyte interfaces and the cathode solid interface. And so basically one is seeing a reductive potential. So you can think about, if you're using a material, you can really write the equation under the reduction. It may take a thermodynamically different pathway for reduction to give different reduction product. If you do oxidation, it's a whole different game. It may decompose into a different, if you use the same material and produce different instabilities, which I'm focusing. So keep that in mind of anode, which is a lithium metal usually, or it can be anode free, and a solid electrolyte interface. And then let's go back to our, whether solid state physicists call it Fermi level or chemical engineer call it at chemical potential. What exactly we mean that there is no solid electrolyte which is thermodynamically so wide and stable to cover both anode and cathode. This is basically based on an electronic band diagram picture, but let's assume you know the semiconductor physics well, but now you have to also include ions in it. Okay, so it's not only necessarily of electrons and holes, but in terms of ions and electrons. The ideal picture is, if you don't concentrate on this dotted line, is that there is, if you have a solid electrolyte which has a HOMO-LUMO, that means it has a oxidation, intrinsic oxidation and reduction potential, valence band and conduction band, you can think about it. And then depending on the cathode and the anodes, here is a lithium metal, which has a potential Fermi or chemical potential, you can say, of the anode at non-reductive stage. And then we have a cathode, which is have a stable HOMO-LUMO gap. Ideally speaking, there is no solid electrolyte which you can expand, cover the cathode and anode together. So basically what happens is, when there is a redox phenomenon, there is always a kind of decomposition or interface formation, and that defines the effective chemical potential. How this sort of, you can think in terms of band alignment. People who do semiconductor physics can think in terms of how the band bends to make the Fermi level adjust. So it's a similar kind of things, which definitely, depending on what interface they're forming, the electrochemical overpotential is determined the difference between the band. So basically, when you start electrochemical activity, redox activity, the chemical potential sort of align themselves in terms of the interfaces formation, which I'll come into the bulk of my talk. But this is the precursor. People who are not doing solid state batteries and things, this is a kind of precursor for them. Now, all the kind of important to talk a little bit about the thermodynamics versus kinetics. Now, as I told you, that you can calculate the effective oxidative stability and reductive stability. Why that is important? Because it dictates the interface that is formed to, as I said, to make a functional battery. And there are a lot of details in that. I don't want to go into the details, but our friend in Maryland, IFMO, and a few others have done excellent work using density functional theory and to really calculate the electrochemical window of a series of important, LLZO sulfides. And these dotted things are basically, here it shows the extended window, assuming this fully dilithiated. So this gives you, people like me and you, a mind about, hey, if I am choosing LLZO or a lipon, where is the oxidation? What is the electrochemical window? Basically where we can use. Because if it is within the electrochemical window and there is a redox process happening, then there is no interface formation. It's an ideal interface, but that usually doesn't happen. The left portion of here are basically the decomposition product, which I'll come when we really start forming the interfaces. We need to know this kind of voltage window of these interfaces that are formed as a function of, these are not practical electrolytes, but it's important to know what's the range it to be. So these are the all essential toolkits we need to understand and appreciate before we go deep dive into understanding the functioning of the solid state batteries and function, which I thought I should try to give in my first 15 minutes of my talk or 20 minutes of talk. Now in the second part, I want to walk you through how in any solid state laboratory we make a material and why, and make a solid state batteries, and then we try to diagnostics understand the interfaces. So today I'm just going to about sulfides. I do other things, but let's go about sulfides, how to design a materials and start making for the sake of students today. Now, the first time when we do a sulfides, a thiophosphates, now it is always good to have a phase diagram in the mind, because you have to make sure that you form thermodynamically stable phases. The metastable phases are okay, but first you have to make a phase pure thermodynamically stable phase. So you make a phase diagram in the lithium sulfur phosphorus and try to find out which are the superionic conductors that as report or you want to synthesize. Or so basically today, for example, I'm going to talk about Li3PS4, but then there is other, if you go along these tie lines, you have other superionic conductors like Li7PS6, but there may be some LiPS3 which may not be also superionic conductor. So you need to know as you're synthesizing that where are you want to based on your stoichiometry. Sulfides are a very interesting class of materials because, if you look at the crystallographic structures, the ionic conductivity actually depends on how these phosphorus sulfur tetrahedras are connected across the edges or across the vertices or corners or like open channel. So this is for a phosphorus sulfur chemist, this is very interesting structure property correlation. But for you, I want to move on to make sure that, when you make a phase diagram, these are the phases, what you want to synthesize and where you want to go along the tie line, changing the stoichiometry for changing the conductivity or what. So the reason I chose sulfide today is because it is earth abundant, except the lithium precursor, which is equally challenging for everybody. But phosphorus, sulfur, they're affordable. But the reason I chose sulfur today is because you can do it relatively. If you're done colloidal chemistry and solution chemistry, you can do this. It doesn't require in high temperature, 1000 degree or 1200 degrees centigrade or more, like garnets or ceramic. You can do a scalable low temperature synthesis by mixing the precursors and stirring and precipitating down and then annealing it. So you can see, you can make a lot of these superconducting things using different solvents, organic solvents, and then annealing the temperature and getting the conductivity here. So you can start making these electrolytes reasonably well. The beauty of the sulfide is that depending on the annealing temperature and the solvent you use, you can get amorphous or you can get crystalline. I think very few system have this flexibility, and you can have changed the semi-crystallinity and amorphous, and sometimes you have the same range of conductivity. That's a very classic model. So you make these things, you monitor the XRD, look at the phases, And then if it is amorphous, it will have no peaks. But then initially when you start synthesizing it, it will be broad, it will be amorphous. Then you start heating it up. And then sometimes if it is amorphous, however high you heat, there is no crystalline peaks, but it's supposed to be crystalline. For example, if you use THF, get a crystalline phase. If you use acetonitrile, you always get amorphous. So this is the beauty of solution synthesis, that you can control the phase purity, you can control the domain size, you can dope, you can put dopants in it. So these are the advantages of doing solution-based synthesis. So after you make this, you have to make sure that you really measure the conductivity in a reproducible and the right way, whether it's a blocking or a non-blocking electrode. You should always get the same conductivity like a textbook. For example, here Li3PS4 between carbon-carbon symmetric carbon-coated aluminum, you get exactly textbook impedance. But there are a lot of details to that, meaning it all depends upon also how dense your pellet is. Because remember, the ion transport and things has to go in between the two blocking electrodes. So sometimes you have to optimize and make the pellet very dense so that you have the right conductivity. So after you make this pellet, thin pellet, then you take a lithium metal, thin lithium foil, and you take a composite cathode. It's a whole different research there on how to make a composite cathode work in a solid state. Today, I don't have any time to say that, but all I want to give a thing is similar to a coin cell in a lithium ion. You make a pellet here, solid state with no drop of liquid. So there is a way to how to make this dense pellet and apply pressure. I'll tell you why you want to apply pressure, because of increasing the wettability or contact resistance, contact area between things. So you make a thin anode and you define everything, how you make the cathode is NMC cathode, and then you start seeing battery feature. Now the first feature that you see is very interesting, and that exactly tells you the thermodynamic instability. When you make this nice pellet, when you do the first charge here, you see a very large capacity, which is good, but you can see this plateau is almost gone in the next features. See, it's not there. So this is because the lithium phosphorus thiophosphate, this one, has only a oxidation stability of 2.7 volts. That essentially means when you start going to 4 volts, this LPS dissociates. And this capacity or this extra thing is an irreversible process that's called LPS redox. And once that does that, you don't see in the second cycle, but the capacity is reduced because you have formed a reactive insulating sort of ion insulating layer, which is reducing the capacity. That's one of the main reasons why. So one has to be very clear understanding of how much pressure one to apply to get this kind of charge discharge. You're almost getting 50% or more, discharge capacity. You can improve on it by electrode engineering, obviously. But I would like to give you how you synthesize it, make a pellet, measure the conductivity, then make this a complete cell, and then it's not perfect solid state, but that's how the field evolves. Now you can change the pressure and see whether you have hit the optimal pressure, beyond which there is no point in increasing pressure, because nobody likes to have stack pressure. If ask the automotive friends, they said, no, we don't want stack pressure. It increases cost, complexity, and weight. We don't want, if it is zero, even very, very low pressure, that's ideal. We don't want stack pressure. But unfortunately, solid-solid interfaces, to make it work, you need to go in some cases at least 5 megapascal of the pressure for sulfides at least. So then you can ask me a question that, okay, NMC is not a good battery. It may be, you want 4.2, you are putting stability at you are using electrolyte which decomposes at 2.7, 3 volts. Okay, so that means why don't you take a high capacity, low volt cathode? Fair enough. So what you do, if you use a iron disulfide type cathodes, which is just around 3 volt, you get very nice reproduce capacity because it's always below the thermodynamical stability of the LPS. So you are not going above 3 volts. You get good capacity retention, good reproducibility, but it may be low energy density. So these kind of textbook things you do to make sure that you really get what you really expect in your electrochemical signature by changing the cathode chemistry. I want to now switch gear a little bit to say what's more interesting. So I gave you an example that LPS is good, sulfides are good. They are reasonably okay with respect to lithium metal, reasonably okay, or you can say that is okay for lithium, which forms a passive layer, passivating layer, sort of pseudo-passivating layer, but it's not good at cathode. So, but you can go to halides, another very interesting class of materials, where showing some predicate which has higher oxidation stability. The reason I am telling you in the drawing board for a material design people like us, it gives you a lot of flexibility of choosing sometimes not so expensive indium like material, reasonably okay to use it, rather than some fancy rare earth materials. So, but again, it gives you also very high conductivity. The reason I am interested in this lithium indium chloride little bit or somewhat is that you can make it not using organic solvent. You can make these phase pure in a water-based synthesis. So you take these precursors and mix it, and then very controlled heating. As I can show you, the controlled heating, it has a water of crystallization, and then you heat it and you form phase pure lithium indium chloride, which has already a conductivity of 10 to minus 3, water-based. Unlike the sulfide, which was always a acetonitrile or THF or organic solvent. And organic solvent can be toxic and expensive as well. So this is interesting because it gives a lot of degree of control when you start, for example, start heating 50 degree to 90 degree to 140 degree, very low temperature. You can reduce the water of crystallization of water of hydration from 1.5 to 0.2. You can use TGA and DSC to see what are the anhydrous phases you are moving. And the question is how the conductivity is correlating with heating, because you expect when more and more water loses, the conductivity will increase. And that's exactly what's happening. If you are doing really good at impedance, you can monitor the real part versus imaginary part. You can see as we are heating, there is some nice signatures here which correlates to the impedance becoming lower and lower and lower. So you can see this is a very high impedance when high water hydration, but once you start heating in the right process, you get very nice bulk resistance. There are grain boundaries. You can control these grain boundaries by controlled heating. So anyway, today it's not a synthesis topic. I can go more on that. But if you do halides, which has a higher oxidation limit, combined with sulfides, which works better with the lithium metal, and then still take the NMC cathode, which I showed you, you can have a nice, reasonably nice solid state cells at a lower current, obviously. I'll come back to high current and fast charge later, that Parthas and all our groups are all working on with us and others. So bottom line is, no one solid electrolyte is perfect. You need to combine the halides with sulfides, different oxidation and reduction stability, make a sort of bilayer filling, take the high voltage NMC cathode, and here it is shown for indium. I'll tell you why. But then you have a functioning solid electrolyte, solid state battery with not a drop of liquid electrolyte. One example. Now, I want to walk you through a little bit more. You can say, okay, these are all lab scale things, small scale things. You can always do that, but can you scale it up into higher things? In my group, in my lab, we are always making the real composite electrolyte with high ceramic loading. And that's where the real direction and value is. In a way, if you see, you can make really composite electrolytes with commercially relevant materials and do really good plasticizer and salt and you can process it and can make roll to roll high ceramic loading O'Hara based electrode. Just one example. We also have things in the lab where as can make polymer composite electrolyte. You can take a ceramic and then sinter the ceramic to control the grain sizes so that each neck is connected to other neck. And then that gives you the mechanical robustness, but they're brittle. And then what you can do, you can start filling the cross-link polymer and cure it. So then you have a polymer ceramic, high conducting, controllable thickness, interconnected, scalable, 3D interconnected composite film electrolyte. So these two examples are saying that we don't only do lab scale, bench scale things, we try to see the feasibility of scaling it up using spray coatings and doing through processing and large scale potentially large scale parameters, but not compromising on the conductivity that we can get. All right, so last part of my talk, I want to give you a little bit on more controlling the interfaces and interphases of solid state batteries. So I showed you the big picture, I showed you the stability regime, I showed you how to make it, how to make a device, what are the boundary conditions, how to make a functioning cell. Now let's go a little bit more deep dive into interfaces and interface. What are the guiding principle? What we are looking for? Now, Yannick has a very excellent review. I would encourage to read. So this is again coming from people who have done solid state physics very easily, and also even lithium ion. So ideally, when you have electrode material, lithium metal, and a electrolyte, assuming it doesn't react each other chemically or electrochemically, you get a perfect stable interface, and that doesn't happen usually at all. So always lithium is very reactive. So IAC stands for a inorganic solid electrolyte. It's lithium, and you can see it's perfect. But this is a perfect case one interface where nothing happens, you can hear. But usually many times what happens, these interfaces of a solid electrolyte and lithium metal, they react with each other. And then what happens is it's like a slow corrosion reaction. It grows. And what happens is it forms a mixed ionic electronic. And the electronic current, that electrons get localized in the reactions, and it forms as a precursor to grow. So that this reactive interface is always growing with time. And that's not a good thing. It's just like a corrosion current or corrosion that slowly takes out all the charge and lithium and consumes the lithium and all these things. So this is one case of interfaces which you want to avoid. Other one is called passivating interfaces. What happens here, the interface first reacts and forms a decomposition product. After that, it stops, still ion conducting, but there's a catch there. So you need to make sure that your inorganic solid electrolytes forms almost a product, one uniform product here. So there are two cases here. One is a composite decomposition. For example, if you are using Li3PS4, as I give very simple case, as I tell you, when you go to reduction at lithium metal, it forms lithium sulfide and lithium phosphide. Lithium sulfide, we don't want actually. It's always electronically insulating. It increases the resistance. We don't want that, but it's unavoidable. But luckily, what happens is the lithium phosphide phase can form this kind of domain so that it's very highly lithium ion conducting. So it forms a low resistance, nice, and lithium sulfide here is purely electronically insulating. That works out well too. But we have to make sure that there is the ions have a good path of going there. But the ideal case would have been just only one kind of decomposition forming here. So there is no multiple phases formation here. So these are the very fundamental things one has to think about when you are designing the right in terms of chemical reactivity and electrochemical passivation. All right, so So now let's come back to some other inner workings of a solid state and battery and what we are looking for and how modeling theory and interfacial design, we need all this knowledge together to solve this problem. Now I'm going to have give you a little bit of flavor of the stripping versus plating current density, what you're looking for basically in a lithium solid electrolyte interface. Now, as I said that if you take a sulfide based, this is typical chloride based argyrides electrolyte here. Now you start always with the lithium metal and lithium and electrolyte, T is equal to 0, nothing happens. Now you start stripping. When you're stripping means the lithium is being pulled away through the electrolyte to the other side. Now what happens is when you start several stripping, it's not homogeneous. You start forming voids here. Now what happens after stripping is plating, right? That's how charge discharge work. Now when it starts plating after this multiple stripping, the lithium comes back, but it doesn't fill in the whole void here. Okay. So then in the middle of the plating, you can see this is happening. But then at the end of the day, if you start plating long time, it comes and plates on top of this, but it also leaves this area out here slowly. And what happens that ultimately such things, there is isolated voids, which are like gas bubbles. These are not good because you are losing the continuity here and increasing the area specific resistance. Now you keep on functioning the battery and the contact areas between the lithium and the solid electrolyte is become worse. So we have to make sure. So how to solve these issues? That essentially means that we are taking out lithium at a finite rate. That means lithium can come from the lithium metal. We have to pull this at a faster rate so that it's not depleted at the junction here. That means we need to have increase the self-diffusivity or some kind of fast lithium transport to fill in there before it's depleted by the solid electrolyte. That's one of the way to think about it. And this is the limitation. So usually it's not the plating current, it's the stripping current density that actually, if you are designing a fast charging or increase the more current density, it's the stripping current density that is actually important in this kind of scenario. So how do you increase that? How do you increase the rate of mass transport of lithium metal? One way, if you just bank on the lithium self-diffusion, it's not going to work out. It's such a very limited diffusion. But there are many ways: self-diffusion, there is creep, there's plastic deformation. And so you can take out the lithium creep. Lithium creeps very well if you put a stack pressure. So no wonder why you need a stack pressure, because the more pressure you put up to some regime, the creep rate will be more. So you can compensate for fast diffusion. Or you can alloy the lithium metal, and it increases the self-diffusion, but it may not increase the creep. So these are the techniques and knobs you face, to really address this rate of mass transport issues here. Another thing is, what are the critical parameters based on the plating current density here? Now, there are some studies, it's very interesting studies now, because plating current density is also, it comes back, and that's where the dendrite formation happens, right? If you see a lot of voids, everything, and then it's plates and plates and plates, there's overpotential, and slowly at some point there is a formation of filamentous growth, and that can short it. So basically what people have started doing is they found out that if the lithium is of micron size, has significant high yield than bulk lithium. So instead of using bulk lithium, you can have this kind of micron size lithium has higher yield strength. Or as I said, you can increase the fracture toughness of the solid electrolyte so that you can have more higher plating current density, because that's how we need to increase the rate capability. High stripping current density, that's critical for high rate, and also we need to optimize the plating current density so that there is not much polarization between the plating and stripping. the over potentials not increase. So there are many ways of doing it. For one example is go to this composite solid electrolyte that I just mentioned. So I'm going to show you that sometimes, despite all this nice theory and fundamentals, things don't work the way we want to. For example, as a friend Matt has shown before, a long time back, so a while back, a couple of years back, that if sometimes to TEM, you see that sometimes instead of forming these intermediate unstable products, you see formation of amorphous phases, not crystalline phases, by TEM, in situ TEM, and there is volume expansion. We never expected that thing, that when you have this decomposition product, they will have a net volume expansion, and that can create some stress. And so that thing, that interface formation is sometimes a failure mode, and it has been clearly shown that. Last 1 or 2 minutes, I want to come back to the cathode solid electrolyte interfaces, because cathode has a whole unique issues at the solid electrolyte cathode interfaces than the anode one. And this cartoon made by one of my group member tells you what are the solution to these problems. It can be space charge layer, it can be microstructural degradation, volume expansion, so it's cracking, and cation heteroatom interdiffusion. And then the way to solve you go about is by coating or buffer layer by ALD, or you can change the composition, and or you can use a zero strength cathode material which has minimum volume expansion. So these are the sort of fundamental processes that we need. And nowadays, using beautiful top spins and XPS, you can really see how in a 3D in a porous cathode structures, you can see or a dense cathode structure, you can really see that solid electrolyte are getting decomposed as you cycle around. So this is NCM. But when you have zero cycle, there's hardly any decomposition of the electrolyte. But once you start putting things in only 3 volt stability, you can see using TOF, SIMS, and XPS, the cathode particles are surrounded by these interfaces. Now, the quality of these interface defines the properties of the cathode solid electrolyte, and hence the solid electrolyte solid state cell performance. So there are many ways of overcoming this. One way, traditional way, is to have nice coating of the cathode so that there's a buffering there, and so the lithium comes in nicely without forming a resistive phase here, and you can sort of reduce the electrolyte not seeing the cathode surface, and that's a good thing, and people have done that. Just want to tell you for the sake of your completeness, and it shows by when you coat it, it's much better stability, much better coulombic efficiency, obviously, because the area specific resistance and the decomposition of the electrolyte at the interface is reduced. And there's tons of understanding that, but there's still lithium niobate is okay, but it's not ideal. This is I'll end my talk with a very interesting thing here, is that everything starts at a small level. You start these interfaces, cycling these batteries for a long time at the cathode solid interfaces. It starts with a minor crack or void here, but you start doing this many times, it starts growing and it forms these kind of gaps here. This is a typical case where a sulfide surrounding a meatball cathode, and then it starts with a crack here, like fracture here, and it sort of grows here. And if you can see a cartoon here, is how this slowly, because of the volume expansion and then the cross talk and all these things, you can see the mechanical failure. The electrolyte layer is sort of physically distanced from the cathode. And when this has happened, obviously the battery would definitely fail, 50% capacity loss, and it will just slowly not work. So I am 7 minutes from 1 hour, so I'll leave last minute for talks. I really thank for my diverse team members for making these results, and ask DOE for support. Thank you.